Hello, everyone. Welcome to our session, Demystifying Artificial Intelligence for Earth Science and Bridging the Gap for Non-Technical Scientists. Uh, I'm Sanjana Achan. I'm going to be the host for today's session. And I would like to say that we have great things on our agenda today. Okay. And through the session, we'll be exploring the intersection of artificial intelligence and earth science with a focus on making this complex field assembled to non-technical scientists. Our first speaker for the session would be Nicoletta, who is working as a research scientist at University of Washington. She'll be discussing the revolutionary impact of open machine learning tutorials for geoscience. And I would like to say that her presentation would be a stage for understanding how AI can be harnessed in the geoscience field. Our next presentation is by Johnson, who is working as Research Associate Professor at George Mason University. He will be demonstrating how machine learning playgrounds can be transformed into actionable products using workflows systems like GeoWeaver. Moving forward, Gokul, who is working as Research Assistant at George Mason University, is going to provide a detailed breakdown of remote sensing based snow water equivalent forecast workflow. And understanding this workflow is crucial as it would help you in understanding how real world application of AI can be used in earth science. So without further delay, let's dive into the world of artificial intelligence and earth science. I hope you find this session both informative and inspiring. Over to you, Nicoletta, for our first presentation. Thank you.
Thank you, Sanjana, and welcome everyone to this session. Thank you for joining us today, and I'd be presenting on GeoSmart today, our program at the University of Washington. I'm not sure I'm gonna demystify anything today. However, my goal today is to point you to potentially some useful resources. So my talk today is going to focus on techniques in education, especially on GeoSmart, which stands for Geoscience Machine Learning Resources and Training. It's a program that has been developed at the University of Washington in partnership with George Mason University. I'm a research hydrologist and a data science fellow at the University of Washington eScience Institute. I have collaborated with Jensen Sun from George Mason University, Anthony Arendt, Scott Henderson, Maureen Denal, Stefan Todoran, and Stephen Pestana from the University of Washington, Annie Burgess from ACIP, and many other collaborators. Some I will mention in the talk, and some I may miss, and I will apologize for that. Thank you all for collaborating on GeoSmart. What is GeoSmart? GeoSmart is an educational framework dedicated to advancing machine learning adoption in the geosciences with open tutorials and hands-on training. The motivation was kind of clear to us at the time. We saw high interest in the topic, but limited learning resources for applications in the geosciences. The target audience for this program is beginning to intermediate with a focus on hydrology, seismology, and cryosphere research. The primary funding agency for the program is NSF. The cyber training program awarded us funds to develop this program. The goals of the project are access. Any geoscientist can access and learn from, and also reuse GeoSmart training materials. And there is a link to our website where we host our training materials, and I will describe them in the next slides. The second goal of the program is community building. GeoSmart is attempting to increase the number of geoscientists who are able to confidently apply machine learning to their own research we aim for capacity building at all career stages. And ultimately, the third goal is to embrace machine learning. GeoSmart is also aiming to develop an inclusive research workforce capable of advancing fundamental geoscience challenges through broad adoption of machine learning. And how do we do this? This is I'm going to present on our program structure next. First thing we started to work on was classroom education. And we established a new class at the University of Washington in the Department of Earth and Space Sciences. The class is a 400 level combined with 500 level, which is undergrad and graduate level, a mix in which 70 to 75% of the attendees are at a graduate level. The class has been already taught 2 times at the University of Washington. The second component of our program structure is providing examples of end-to-end machine learning workflows, like really use cases that we are hosting on the website, and we'll take a tour a little bit later. The third part of the program is organizing and hosting collaborative coding events, Hack Weeks. The Hack Weeks are events that are organized typically by the eScience Institute at the University of Washington and are comprised of tutorials, projects, and community engagement events. But so all these components of the program are not necessarily developed in silos. They can interact with each other and inform each other. For example, use cases, which are end-to-end machine learning workflows, are a starting point for learners that could provide motivation for what can be accomplished. And they can serve as examples for class curriculum or for class projects or for Hack Week projects as well. Both materials developed in the use cases and in the Hack Week projects can then inform the classroom curriculum. And I would like now a little bit, I'd like to focus a little bit on use cases because this was a collaboration with ESIP and the central part of our program. How did we do that? We found in ESIP an excellent partner to work with and a platform for community building. We collaborated with Dr. Annie Burgess on this and developed a request for machine learning tutorials that we posted on the ESIP website. And within this proposal call, we selected 6 different projects as listed here. The projects that were developed as part of the ESIP cohort are now the majority part of our use cases that are hosted on the website. And they are mostly focused on snow hydrology, geostatistics, and hydrology and climate change, mostly on hydro-cryo side of things, with some other seismology-focused projects being in development. 16 participants have worked on the GeoSmart ESIP use cases. I would like to thank them all. They're listed today here on this page. And 6 different projects have been developed over a period of 6 months in collaboration with ESIP and our ESIP cohort. What has been accomplished within this work? We address classification, regression, and clustering problems with a range of machine learning techniques such as Gaussian processes, linear regression, and ranging towards other deep learning methods and other more sophisticated machine learning approaches. And the packages that were used were scikit-learn, PyTorch, TensorFlow, Keras, and other major packages that are being used currently for machine learning problems. Now, I think I'd like us to take a tour And if we click on this link, you will be taken to this use case. You see here a cartoon by Dr. Oriana Chegwinden that you'll find on the use case website. This use case was developed by Drs. Andrew Bennett and Oriana Chegwinden and featured at AGU this year. And I think I'd like us to visit the website now. I'm just gonna go here. I hope you can see this. This page hosts our use case library. This is the GeoSmart website. If you click on these tabs, it will take you to the different parts of the program, as I mentioned earlier. But if we are talking about our use cases, here's Andrew's and Oriana use case, and I would like I'd like to show you what is it about. This link will take you to the Project Pythia Foundations to learn more about the packages and techniques used for data preparation. And diving into the machine learning part, if you click on these links, it will tell you the story about each of the use case. What is needed to run the use case? What is the background story, the scientific story of this use case? Why specific packages were selected, and so on. How everything was implemented and configured. How did we train the data, the model? And then how did we run the model? So I would encourage you to browse these use cases, and hopefully you'll find them useful. And going back to our program here, I'd like to maybe continue with the second component, which was the Hack Week, the hands-on training event that we hosted at the University of Washington, October 23rd to 27th. It was a hybrid event, in person and online, with a focus on the hydrology and cryosphere. And this, the figure on the right, it really shows Dr. Ryan Johnson, who was one of the project leads in the ESIP cohort. So ESIP not only facilitated community building and the development of use cases, but also that engagement continued with ESIP cohort participating in the Hack Week event. And what is this Hack Week really? I just wanted to talk about the eScience Institute Hack Week mission, which is to provide hands-on opportunities for participants to learn the tools of open source science in a welcoming and collaborative environment. It also provides opportunities for community building, accommodating various backgrounds and career levels. Hack Weeks are co-creative, which means that the eScience staff works with the community partners to develop tutorials and hands-on project work. They are interactive and immersive, and they are conducive to open source science, which means the projects and science is available on GitHub. So as I said, for our GeoSmart Hack Week, we started to think about how do we want to present or organize this event. We did have tutorials. It's just an example here. How does the neural network work? But we also considered a more focused approach on the Hack Week projects, which we see as a primary tool for immersive learning. A Hack Week project is a 68-person team collaborating on a well-scoped data science challenge supported by helpers. And participants really can gain experience in working in teams, build software and advance research, or deepen understanding of a particular topic. Also, it's really good for networking and meeting new people and ultimately having fun. And so we did host this GeoSmart Hack Week, And we had to think about how we want to balance the tutorials with project hacking. And there is really a delicate balance of how we want to deliver the content at these events. Sometimes there is too much, sometimes there is too little. Sometimes you have to think about how to prepare the participants to gain what they wanted from the event, like learning to use data, learning to use tools, learning to train and use a machine learning model, and also reuse and reproduce the results. For this hack week in particular, we did focus on use cases as a learning tool. We started thinking about creating ample space for open project work, and we chose to design the hack week as for intermediate cryo and hydro practitioners. And how did we do it? For pre-hack week events, we wanted everybody to feel comfortable at our events, regardless of their prior knowledge of Python, machine learning, or data handling. So for that, we offered the opportunity to the participants to sign up for software carpentry training that was organized at University of Washington eScience Institute prior to the hack week. And during this event, participants got familiarized with Python workflows and data handling. Also very important, working with GitHub, Git and GitHub. Also prior to the hack week, we established a team that worked to identify project ideas and project leads in advance. And why did we take that approach? Because a lot of the machine learning workflows is data preparation and data handling and getting the data into a machine learning format. So we wanted our participants to learn how to use a machine learning tool at the hack week and not spend too much time with data preparation. So we worked in advance with project leads to set up project repositories and populate them with machine learning ready data sets. And at the hack week, we did work collaboratively on projects using machine learning packages because we had the advantage of having an in-progress project and the data close to being at least machine learning ready. And post-hack week, what are our ideal expectations? We ideally would like to see the formation of a community of practice. We'd like to see projects to continue with a concrete outcome, software packages, publications, and presentations. And we would like to continue working with the project leads, eventually turning all the hack week projects into GeoSmart use cases. I'd like maybe now us to go on the hack week page and explore a little bit what's there. This with the idea that if you would like to, let's see where it is. If you'd like to explore what has been developed at the Hack Week, please go on this website and click on the event Jupyter book. Here you'd see all of the resources that we used in preparation for the Hack Week, including the skills refresher. But I would like to point you to where the projects are, with projects roadmaps and how we initialize and set up projects. And this is a list of projects that were developed at GeoSmart Hack Week. And if you click on the links here, it will take you to the GitHub repository if you'd like to learn more. Back to our presentation, I'd like to acknowledge our online participants. We wanted to accommodate participants who could not travel to the University of Washington, but wanted to get experience with machine learning. We accommodated about 20 participants online. And I'd like to thank them for for their patience and for their contribution as well. We benefited from community support, which I also would like to acknowledge. We use the Jupyter Hub built for NASA cryosphere communities in partnership with the International Interactive Computing Collaboration I2C. Tasha Snow in particular, I'd like to acknowledge her for presenting on CryoCloud and Jupyter Hub and working with the Jupyter Hub at the Hack Week. The overall goal for CryoCloud is to establish a curated interactive computing platform for the cryosphere community, and also develop expertise in open source software and cloud-based platforms. We also like to thank our quasi partners who came to the event and helped various teams with data that is hosted on the quasi platforms. For example, output from National Water Model and other data sets that have been used in projects at the Hack Week. I don't know if I have more time, but I would also encourage you to go online on our website and perhaps browse our open curriculum. The class curriculum that was established at the University of Washington in the Department of Earth and Space Sciences. Doctors Marin Denal and Akshay Mehra taught this class this year. And I would at least would like to point you where this sits on our website. If you go on the landing page, there's various tabs that take you to the various resources that I showed you today, but this is where the class curriculum is. And if you click on the first link here, the curriculum is open for any teacher that might be inspired to browse and reuse this content. I think if you'd like to learn more about the classroom curriculum, please go on the website. But really briefly, it has topics on open science, ethics, and practices. Learn about the data sets, data structure, and modalities. Learn about statistical learning, machine learning, classic machine learning, and some deep learning. And then really, in the end, it's about deploying large-scale machine learning and learning the computing skills for that as well. I would like to take this opportunity to invite you to contribute to GeoSmart. Again, if you go on the website, you'll see a tab that says Get Involved. We've listed ways to get involved with us in various parts of the program, either contributing to class curriculum or Hack Week, or to the Hack Week, or if you have a beautiful use case that's ready to be being showcased, please get involved. Send us an email and we will showcase your use case on our website. Again, thank you to our sponsors and to our collaborators for making this program successful. I think I'd like to end here. Thank you for your attention.
Thank you, Nicoletta. That was a wonderful presentation. And before we move on to the next presentation, I have a live interactive poll up for you guys. You can either use your phone to scan the QR code. I'm just pasting the, or else you can just use the link which I'm pasting in the chat window to take on the poll. So the question is, how effective do you find the current available machine learning tutorials, especially designed for geoscience, in meeting your learning goals? Okay, I'll quickly move on to the next question. Rank these potential challenges in adapting machine learning tutorials in geoscience. You can just drag and drop them in the order which you like. You can use the same link. I hope everyone answered the question. I'm just quickly moving to the next question. What is your preferred learning format for machine learning tutorials? Select all that applies. So I can see that people prefer both online tutorials and open curriculums. Yeah, that's so now I'm gonna quickly move to the next question. Please rank your preferences regarding the structure of machine learning tutorials. You can just drag and drop them. I can see that step-by-step guidance is the first one. So that's what the open curriculum, which Jess Nicoletta spoke about, would provide you. Now I'm gonna quickly move on to the next question. It's a word cloud question. So use few words to describe how machine learning tutorials could impact your understanding of geoscience. So I guess it would be a very great impact in your research work. Okay. Now we have Johnson who's gonna talk about this, who's gonna present next. Over to you, Johnson. Thank you.
Thank you, Sanjana. Let me pull out my slides. Okay, yeah. Hello, everyone. My name is Zhen Sun. You can call me Jensen. I'm from George Mason University, and I think I know most of you. So, yeah. So today we are talking about how to like for the researchers who are interested in AI to start with it. And for people who already working on AI, thinking about how to operationalize your work. It's not just always stay on the prototype stage as feel like disconnecting from the real world AI progress. I think that's very important because we have talked a lot about like regulation, like ethics, or how much the impact AI is going to have on all of us. But really, not everyone know how it works. It's like if you want to regulate something, it's better to understand how it works, right? If you want to regulate like the flight industry, like the aerospace industry, you have to understand how the plane works. It's the same thing actually. So right now, only a handful of people know how AI works. It's like a computer science, the computer science experts, and all those people who are in the tech world. Outside, outside that small world, most people actually don't know how it works. And that is actually a problem because we have talked about like democratizing the AI for a long time, but most people are still like, we are based on their understanding of the AI in the science fiction novel. So it's not a bad thing, but yeah, most of the ideas actually doesn't match with the reality here. So that's why we put together this session and talk about like how to just let everybody see how it actually works right now. So yeah, that's why we're like I'm presenting GeoWeaver. GeoWeaver is actually at the central level. So most people say, hey, what all this AI stuff has to do with GeoWeaver? Well, I will explain that later. So I would love to first like acknowledge all the contributions from our amazing collaborators, Coco, Nicolata, Annie, and Marshall, and many other contributors to the GeoWeaver project. And also we have a lot of support from the community. Like without support from NASA, NSF, and NOAA, this GeoWeaver will never exist. So thank you all. Yeah. So first is what is GeoWeaver? It's actually a workflow management. So you probably have heard a lot about like a workflow management, but not everyone has it. It's like it's a handy tool. It's like if you want to build a big project, you have to put out, to purchase or get a lot of useful tools first. Otherwise, using your own hands is just impossible. So GeoWeaver is such a tool that helps you to manage all your work. Basically, it will help you to keep track of everything you did, and then you can easily pull out and export them and share with everybody else. So the whole community can actually work on one single project without losing anything. That's actually a very serious problem right now because AI is it's so random and everybody just change a little bit and it's a new work and new results. And who is going to check that? Nobody. Basically, one student or one research did something for 6 months, left, and then the other people just start over and met all those issues the first person met before. So there is a lot of duplicated efforts all over the places, and then nobody just have the good solution. So that's why we use GeoWeaver. And the history is we have this idea back in 2018 and talk with Annie, and we have this eSafe Lab project funded, and we start developing this software since then. And right now, I think it has been maturely running some operational AI models for the past 2 years, and it's pretty good. It's really saved us a lot of time for a very small team like us, like 3 or 4 people, and one time has maintained 3 AI products, basically almost operationally, running every day, and it never breaks down. Even if it breaks down, it's small changes, and even people come and go left, it doesn't impact the AI operation. So it's pretty good tool for small teams like you and me to do some real AI stuff. It was funded by NASA in 2019. It's a access project, and also funded by NSF together with Nicolada by the geoinformatics and the cyber training in 2020. And recently funded by the NOAA. Actually, I'm just a QI using GeoWeaver to help them to forecasting the wildfire. And it's not forecasting wildfire, it's a forecasting wildfire behaviors. Let's say that. So wildfire is kind of random. AI is not designed for random stuff. So yeah, that's a brief introduction. And then we recently have the PyGeoWeaver, which is a Python wrapper of the tool. So you can use GeoWeaver in the Python right now. It's actually still using, underlying it's still using Java to run the engine, but in the interface, the Python will take charge. So you will feel no difference than running other like a Python package. So comparing to the Jupyter, so most of the time we heard confusion about what's the difference from the Jupyter I'm already using. It's not trying to replace everything in Jupyter. It's you can use it together, but the best thing is so for simplicity, it's still you can start it using one line like Jupyter did. And you can also open it in the browser. It has an interface as well. And also you can just stop it using one line. So it's the same simple, easy, lightweight tool like Jupyter. But it has some very good benefits. It's on the right side, if you run the Jupyter cells, you will see the output right away under this step. But in the GeoWeaver, you will see it on the right side. Yeah, actually pretty simple. It's pretty similar, right? So just run your code in the editor. But the difference is there is a history button here. So we have a history button. We will save everything every time you run that code and save it in the GeoWeaver database. And that database can share it anywhere. It's just 2 files. Or you can just export the single workflow into a zip file. And you can also label them. It's like this time the workflow run failed because some errors, you can just write that notes here. So this is like you are managing all your experiment at a different dimension, but which this dimension the Jupyter doesn't provide. And that is like a high level, high dimension benefit provided by GeoWeaver, which is make it super efficient and productive. The ability to preserve history is really something that at least even a big team, any scale of the team should have this feature under your belt. Otherwise, you will run into a numerous of duplicate effort. And how to use it? Just install this PyGeoWeaver package and start it and open in the browser. That's it. And it's not just a local host tool. It could be used for serious stuff. It's very production oriented. So you can run it in the HPC. We already did. We actually run a lot of code using GeoWeaver successfully in HPC. Actually, right now, every day, we are running a workflow to generate the ozone map for the United States. It's pretty easy. It's like you have to run this SSH command. Oh, by the way, if anybody just confused by all these technical terms, yeah, just feel free to ask, because this is like a demystifying anything you don't understand. So don't be afraid to ask questions. We can provide all the cheat sheets for you to understand the whole thing. It's like it's pretty complicated. It's like a whole tech stack, like from the bottom, from operating system to how you use the resources at the system level, and what software you're using, and what's the result model, AI model, and how do you produce AI products. It's a whole stack. It's a full stack thing. There is a lot of technical terms, and you probably will feel very hard to understand. So please feel free to ask any question you want to ask. Just either interrupt me or put the question in the chat. All right. So why do people need GeoWeaver? I kind of talked about this already. And I think I break out this slide many times before. It's like, it's a reality. It's like there is so many AI papers out there, but most of the operational or even useful AI products came from industry. And from a bunch of people who never studied earth science. That's a weird thing, right? It's like, we have studied the earth science for many years, and ChatGPT somehow just, have more knowledge than any of us. So we actually used AI for earth science for many years as well, but we never did something that impressive. Why? Because there are some bottleneck problems. First of all, I would blame the low fairness and tangibility of AI workflows, because everybody just hold a piece of it, and we don't share very well. Even we share, we only share oh, I missed this, or missed that. And eventually other people just cannot reproduce your work. So your work will be lost. Like it's just a paper, and people have to start from scratch to do the thing again. That is a very low productivity, insufficient. But in the industry, everybody just, the whole company can just jump on their workflow, single workflow, and fix the problem right on the spot. So that's why they are so productive. They are producing, generating, training the models every 6 months. They can do that. But in the academia, it's really hard without tools like GeoWeaver to share the whole thing very efficiently among us. It's not a single team work, definitely not a single person's work. We have to collaborate on that. So yeah, so we need to tackle this like a low productivity problem, definitely. We need to efficiently share the workflow and record all the history, make sure everybody's work is recorded and shared and understood. So nobody in the future will repeat either your errors or run into the same rabbit holes as you did. And also, we need to make it very easy to onboard new people to the AI projects. Yeah, so why sharing the workflow is so difficult? Because the dataset is relatively easy to share. So that's why we have so many datasets out there, but we don't have much reusable workflow. The reason is like sharing data set is like sharing the apples on the tree. You just pick it out and ship it. Sharing workflow is like dig the tree out and ship the tree. You know, it depend on so many dependencies that they cannot just migrate that, transplant it to somewhere else. That's not easy to do. So GeoWeaver is kind of like in the middle to compromise solution to do that, to actually make it work. Even if it doesn't work on your side, you can still see all the history to understand the whole thing. So you probably tweak it a little bit and it will start working again. Make it tangible and fixable. Yeah, this is some like comparison, like, you know, people probably familiar with the technologies and say they're already using workflow management engine, something like that. This is a comparison, like it's actually oriented differently. It's like individual person can use GeoWeaver without problem. And all the other workflow engines like Prefect, Airflow, IGO, it's corporate operation. It's like you have to be like the whole team dedicatedly to work on that. So it's not designed for smaller academic, like a research team. On that sense, GeoWeaver is way better for you to adopt. Okay, some must-have benefits. I think I already talked about most of them: portability, reproducibility, and interoperability. Must-have benefit. Yeah, it basically can just, you know, combine everything. One benefit I didn't mention is that even you have multiple resources like your lab servers, your laptop, EC2 instances, anywhere, like all the computing resources, you will definitely like exhausted by chasing all those, like, oh, I did something here, I need to record and move it to somewhere that, you know, centralize the storage. I have to keep record of it. You don't worry about that in GeoWeaver. GeoWeaver can just run your same code on different machines and save all those input output. Not data, just the input source code and output logs in one place. So even you run your code in many places, you still have the whole record in one place. That is a big blessing for people who iterate on their experiment every day. Yeah, some use cases actually. So I talked about this from the developer perspective, but when you want to, like, you know, put your AI product on the market, the client think in a totally different way. So the client is like, we don't know what we want. You know, when you are designing AI products, actually clients have no idea. It's like when the Ford developing their cars at the beginning, people probably was thinking that, you know, they want faster horses. You know, if you ask them what they want faster horses, not cars, because cars is so new. And that's the same thing here in AR, because AI is like, nobody knows what it can do actually. So the AI developer has to be collected with end users, talking about all those user needs and demands all the time to make sure that your product actually will address the problem people cares. That's another issue. So yeah, this is a slide I talk about, like, you know, AI probably be able to do low-level cognitive research and I think that's from one of the workshop last year. I think I posted the workshop link in the machine learning class channel. It was very good discussion. It's very, you know, mind-opening, I would say. Yeah, so this is one of the GeoWeaver backed workflow, and it's still operating every day. I can put the link in the chat later, or Google if you can help. It's constantly better. It's like AI will produce the ozone map at a high accuracy every day. And this AI model takes the CMAC as input and just output the maps, which we have confirmed with scientists from NOAA. It's obviously better. It's like it will capture all these like missed prediction spots and it will change the whole like a map pattern. It's capture all those like underestimated spots and overestimated spots and make them, more pulling them towards the real ground value. So AI works based on this experiment. I can directly see that the AI actually works to improve your model results. But are we like satisfied by this? Not really, because we believe AI can do better. It's AI can like maybe forecasting the ozone for like 3 months or something, and make it a much better accuracy than the current physics-based model. Maybe they can combine and work together, but I think that will be a big revolution there if we do that. But to be there, and we need a tool like GeoWeaver to support us. All right, so yeah, this is something like a team management. If you have an AI team, and how do you like manage all those like onboarding students, because most of the students on the postdocs in the universities, they only work like 1 or 2 years and they will graduate and go. So our purpose is like make it easier for everybody to know what we're doing and know what they will do, and then make it much easier for them to avoid running into something previous person already did, and you don't have to solve the same problem twice. So when we have the five people team, we actually maintaining the 3 workflows at the same time, and it's all working great. So it's very productive solution for you. And also less explanation communication in the email, Slack, the messages. So because you give them the whole thing and they can understanding them directly. And people come and go and nothing else. This is like from the management perspective. If you are PR or if you are like a team leader, this will matters a lot. It's like we don't want to lose everybody's effort, because everybody's time is so valuable. And once they did something, just click the run button and did some experiment, we want to archive that. We want to record that thing. And GeoWeaver can perfectly do that work. And that thing is like people who left will miss GeoWeaver. So this is, okay, GeoWeaver makes it so easy. So we actually miss it, like thinking about probably use it in their new work or something. People on the team will be happier if you use tools like this. Okay, so yeah, we have some GeoWeaver instance up and running there. If you click the link in the Google Doc we have, you can play around with it. Because I don't know if I have time to demonstrate anything. Like I can demonstrate in the breakout room if you want. This is some links. If you click the buttons, documentation, the source code. Oh, I didn't mention that everything is open source on the GitHub. So if you want to, and including the workflows we are running right now, if you want to get all the source code record and the results, just let us know. Okay. Yeah, how do you contribute? So yeah, everything is on the GitHub. So if you want to like just contribute like 1 comment, 1 doc stream, 1 line, just welcome anyone to work together here. Yeah, the conclusion is like, yeah, we definitely should build the variable and tangible AI workflows using whatever tools we have, and do not duplicate effort. AI is like, it has numerous possibilities. And if you, well, some people say, okay, yeah, I created this like AI model and it's running successfully. Well, congratulations, but that's just the starting. The real work is after you created that model, and it's training like in iterations 1,000 times, and that's the real work. If we can like streamline the iteration, the cycles, and it will actually save you a lot of time. And even the first person did the whole work, you say, oh, this parameter configuration, like hyperparameter configuration already being experimented, the result is not good, then I'm not going to do that, right? So possibility cannot be fully eliminated in AI world. You cannot just trade your time with the accuracy. That's like trade-off is sometimes just doesn't work out. So you have to be very careful about your effort there. And it's definitely the group work effort. So transitioning from one person to another is very important. Yeah, the share your workflow in entirety. So there is a export button. So it will export all the source code, not just one split. It will manage it for you. So you don't have to worry like, oh, I forgot one file. And that file is so key that people receive their work will never figure out how it works. That kind of problem will never be a concern here. Domain specific folks. I know that there is a lot of people talking about large language model. You can definitely train your own language model as well. But for Earth science, we are more interested in the domain specific folks, like a specific model for slow forecasting, for earthquake early singular detection, something like specific problem based models. I think that's the first step. Eventually, we're going to create a general AI model for the whole Earth science, but right now, we're not there yet. Error reduction, I think this is more technical. And we, even I and Pablo edited this book with some tutorials, and the tutorial example also on the GitHub. So just feel free to go there and check it out. And if you run into any issues, well, people always do, just let us know. Because with sharing knowledge through the notebook always has that problem. It's like if you click the wrong button, nobody knows what happens. I think the GeoSmart online curriculum, you can already cover that very good. We are working on the papers because I think Susan already mentioned that what we can do. Everybody only has 24 hours a day. What we can do to contribute to the RCI effort. So in the machine learning science, machine learning cluster, we are focusing on either collaborating with everyone there to write some papers. The paper is more like a guiding the whole community and to save time, like to not spend too much time on something that you will never figure out. Just save the valuable time and focusing on something that what we can do, we can achieve. So I think the paper is really good. Like the white paper, the research paper, or over review paper are very valuable. I think that the effort is gonna save many people's effort, duplicated effort actually, and guide us to a better solution together. So welcome to join us. It happened every third Friday at noon. Yeah, that's it. That's the whole slides, and I'm not sure how much time. Oh, I don't have time, so back to you.
Thank you, Johnson. That was a wonderful presentation. Now we'll have breakout room session. So, for the participants, this is the opportunity for you to engage with the speaker, share your thoughts, and raise any questions or doubts that you have. So today we have 3 breakout rooms. The first breakout room, Nicoletta will be there in the first breakout room. You can ask any doubt you have regarding her presentation. The second breakout room, Johnson will be there. He's gonna, if you have any doubts, you can just ask him, and he's gonna explain more about PyGeo waiver, and there's a survey waiting for you. That survey is really helpful for us as we are writing a paper on GeoWaiver. Your inputs are really valuable. And for any other question, you can join onto the third breakout room.
All right, hello everyone, welcome back. You all waited until the very last second to join, so I take that to mean that you all are having some fantastic conversations. Sanjana, are we back to you?
Yeah. I hope everybody had a great conversations in your respective breakout rooms. Now, Gokul gonna present his topic. So over to you, Gokul. Thank you.
Hi everyone. So today I'll be talking about snow water equivalent. So this project is built using GeoWeaver. So this is a use case, a successful use case that actually runs every day to produce a SWE map of the Western United States. So uh, the workflow is completely built using Python and Bash scripts. And before I go ahead and explain about what the workflow is about, let me talk about what is a snowpack. So a snowpack is basically accumulation of snow over an area over a period of time. Now, this also includes the snow depth, the water content in it, and also the amount of snow accumulated. So, so what is the difficulty with uh, measuring the snowpack? So, depending on the region, snow varies from place to place. It could be light, it could be heavy, and it is not easy to measure snow in, say, a hilly area with harsh weather conditions. Uh, so how does this relate to SWE? So SWE is snow water equivalent, which measures the water content in snowpack. And the way how we measure SWE is the snow inches times snow density, which will give us the SWE. So the challenges to measuring SWE is also the same as measuring the snowpack. So the importance of why we measure SWE is it helps us manage water resources in an efficient way, helps us study about climate, the water quality. So now that it is hard to get up to a hilly area with harsh conditions, wouldn't it be nice to have a way to predict the SWE using data that is readily available? So that is what the entire workflow of SWE is about. And so since SWE is the SWE workflow is built on top of GeoWeaver, so this is how it looks on the GeoWeaver interface. So the SWE is just a set of processes that is that actually collects the training data. And it also has the processing, it has the modeling, the visualization, and uh, also the code to produce the SWE map and also deploy it to a website. So this is from the start to the end using GeoWeaver, going from this very beginning to the production. So what is what all things does the workflow use as data? So first we have DEM. So DEM stands for digital elevation model. So this has all the terrain features that we have to take into account. And then we have GridMet, which actually takes into account the meteorology data. And then we have Modus that we're using as for FSCAR for snow cover. And we have Snowtel, which provides the ground truth SWE values, which the model is actually supposed to predict. And then we have AMSR. So AMSR is also provides us a SWE value, which is actually taken from the brightness temperature measurements from the AMSR sensor. So the outline for the entire workflow is we actually collect data and we perform cleaning. And once the data is clean, we have all the features that we require that we are taking into account to be combined using a tool or a library like Pandas. And then we actually give this data to a machine learning model. So this is like the basic outline, but there's a bit of technicality involved and how we engineered the how we did the feature engineering. So now I would like to go into each and every one of the features and show you how it looks. So the first one is the digital elevation. For this, we used a 90-meter SRTM digital elevation. And it gives us the features of elevation. This is how the elevation map looks, and this is how the aspect map looks. And it also gives us northness, eastness, and slope. So this helps the model to better understand the terrain data of how elevated a place is, because location can also like greatly affect how much snow can be formed. And then we have GridMet. So GridMet is basically, as I said earlier, meteorological data. So it has these features of air temperature, minimum air temperature, maximum potential evaporation, mean vapor pressure, relative humidity, and precipitation and wind speed. So this takes into account all the meteorological uh, features coming from GridMet. So this is actually taken from the climatology lab. Then for the modus and AMSR, so both are related to the SWE. So modus we're using as FSCAR, which actually determines if a place has snow covered or not. Also this same for AMSR, which is for which actually provides the SWE value based on the brightness temperature. So for the modus, we're using 500 meters sinusoidal grid. And then for Snotel, so this is the ground truth values that we're using for the sweep prediction. So there are about, in the training data, we have about 700 of these stations in different areas. So this is also provided as the training data to the model. Next, coming to the data pre-processing. In terms of data pre-processing, we are using about 10 years of data to train the model on different locations to show it both the start and end of the water year. And then we have the data pre-processing where we convert the different file formats, because we have a different set of uh, features to work with, which come in GeoTIFFs, H5 and CDF files. So we actually converted each and every one of them to a CSV file, which is more convenient to handle. And then we actually merged all of these CSV files into a larger CSV file. So that would be for the AMSR, we have the latitude, longitude, we have date. And for Snotel, we have latitude, longitude, date. And the digital elevation, we have latitude, longitude. And for modus, we also have latitude, longitude, and date. So we actually tried to train a model on this, and the results were not that good when we actually compared it after the feature engineering, what we were to accomplish. So once we had a CSV file that we could work with, so the next thing is how can we feature engineer this data to make the ML model better understand the patterns. So the first one is converting the data to time series. So for time series, especially for the first thing we focused is to fill in the missing data. So there are good libraries like NumPy that can actually provide helper functions to interpolate the missing data to maintain continuity. And then there is the lagged columns. We basically created multiple columns of the same feature so that we can track it over time, which makes it, which gives it the time series so it can track it better. Next, we have another important thing that we did for feature engineering is cumulative data. So cumulative data is basically when we start at the start of the water year till the end of the water year. And we basically sum up all the values for that each feature. So that actually gives us some good insights and a pattern for the machine learning model to learn from. So this is the start of the water year. So as you can see on the left side, you have SWE, and this is like the day of the water year. And we have a proper pattern like the peak of winter where there is a lot of the SWE value is high. So this is the kind of pattern we were trying to generate with cumulative data. So before, when we actually tried to train the model without any cumulative data, the results were a bit on the lower side. So once we have the cumulative data as well as the non-cumulative data, we were able to see a huge improvement on how the feature was important in able to predict the end result for the model. And now for the entire training data, the entire training data is split into two parts. So the first part is directly coming from the SNOTEL stations, so the ground values, and the next one is from the FSCAR, where we use MODIS to see if that value at that place actually has any snow. So if MODIS reports that, I mean, in the MODIS data set, if we get that there is no snow in that particular region, we actually make it 0. So this is a plot of all the stations in our training data across Western US. Yeah. Next, for the model selection, we actually have extra tree regressor standing at the top. So we used a Python library called PyCarrot. So this actually helped us quickly figure out which model works best with our data. So we just gave it like an year of data, and we just asked it to fine tune it and run the data on all possible models that are available on scikit-learn, and extra tree regressor stands on the top. So that is what we ended up using. So this is a complete breakdown of the workflow of how it looks on PyGeoViewer. So the bottom part is the testing part, where we have GridMed, SNOTEL, the digital elevation, FSCAR, and all of these are actually being merged into a testing data integration. So this runs like pretty much, I mean, this runs every day. And so once it collects all the data, it actually merges it into the CSV file, where it can actually use the model to make predictions. So on the training side, we also have all other same things. So we have AMSR, we have SNOTEL, we have GridMed. All these are all these collect data for like 10 years, and they like merge it into a data integration process. And then we perform the time series conversion, sanity checks, and we get the data ready for training the model. So we actually tried a couple of models. So this right side top area is completely about model creation. So the ET model, which is here, actually stands out. So we are currently using this to actually run a prediction, which comes from the daily testing predictions, to convert it to an image. So the model performance. So this is how the model performs. So we see a significant increase in the sweep prediction after we have implemented the time series and also the cumulative data. So we have a good score currently, and we are constantly trying to improve it with better feature engineering. So this is how the results look. This is also accessible on the, this is the complete workflow is actually deployed onto a link that is right here. You can actually visit this link. I'm not sure if this is visible, but so you can actually go here and like select the date of which the predictions happen, and you can just press load, and you can see the different SWE maps. So yeah, that's it. Thank you.
It was a great presentation.
Yeah, I think we only have 1 minute, so Sanjana probably can just wrap everything up. Sorry, I used too much time.
I really want to thank everyone for joining our session, and I encourage you all to take the survey, which is in the meeting notes, BioGeoWaver survey. It would be helpful for us in writing one of our paper on BioGeoWaver. And once again, thank you everyone for joining our session, and hope you all like it, really enjoyed it. I hope you all enjoyed it. Thank you. Bye.